your parents are like me and are going to take advantage of this warm weather to put up the Christmas lights?
I hate warm weather.
Just a couple?
Because it's not cold.
What I don't like about warm weather is it makes your face all like, you know,
Sweaty?
yeah. I want to. And like you look up in the sun and like it's like burning your eyes. It's like, you know, it hurts. You know?
That's why you use a telescope.
It's
It goes so much faster.
It's a dangerous world out there. But in terms of circuitry, and like I'm putting my Christmas lights up today, because it's the last warm day, and I'll tell you, when I was a kid, I have so many memories of my dad having me help him put up the Christmas lights, and it always seemed to be like -10 out. And I got small fingers, you know, and it's like, it doesn't take much for them to get real cold and lose feeling. And I have a lot of memories. Same problem? Right? Yeah. And it's like, that hurts. Because when you lose feeling, yeah, the pain goes away, but then when you finally get feeling back and you go inside, it hurts like crazy. What's that? They get itchy. It feels all weird, yeah. So anyway, now what I usually do is the next warm day after Halloween, I go out and I put my stuff up. So that is today. Looking forward to doing that. Hopefully before the sun goes down. It seems like it gets dark real fast. What house is this? Can anybody tell me?
Is that the house from Home Alone?
Nope. Christmas Vacation. Yep. Classic Christmas movie. My family and I watch it every year. So, again, this Die Hard, classic Christmas movie right there. I love it. I like those really good action-packed movies. Why did the screen not change? It must be.
I love that movie. I like the second one's fun.
I just had it. There we go. Okay. So, you will not be tested on this. Listen up, guys. You will not be tested on this. There will not be homework on this, but I challenge you to try and keep up, and if you have questions, ask. By the end, if you can get through all of this, and you can understand how it works at the very end, it turns into like university level stuff. So I just want to give you a little taste of it, and if you can hang on to your seats for that long, I give you a lot of credit. So basically, this is a circuit. You've got a wire, you've got a light bulb, and you've got a battery. And that battery has electrons, and those electrons go through that circuit in what we call a current. And a current is just a flowing charge. You can think of an analogy to current being like water going through a pipe. So your current is constant through that circuit. We measure current in amps with a capital A. Resistance would be an example of a light bulb here. The idea with resistance is it's something that the current encounters, and then it does work on that object to cause it to do something. In this case, the current goes through it, and it makes the light bulb light up. It's kind of like you've got water going through a pipe, and maybe you've got a little turbine there to make hydroelectric power or something. That water is doing work on that system to provide electricity. So that's the sort of thing that's going on with a resistor. It's usually a light bulb or something that is flipped on or off. And then you've got potential difference. You can think of it as just voltage. Your battery produces that voltage. If you look on any battery, you'll see how many volts it is. And that's the voltage that is imparted to your system here. So, the main equation for everything we're going to talk about today is this. This is where we live. Voltage is equal to current times resistance. V equals IR. Everything kind of comes from that. Now, this is a common, very basic circuit. This is what you'd learn on day one. This would be your battery, your voltage, plus and minus, would be like plus and minus end of your battery. Current is traveling through this, and then this little squiggly line that looks like Charlie Brown's t-shirt, that's how we represent resistors on a circuit. Everybody with me? All right. Yeah, so
Ohm is where the heart is.
That's right. So if we want to figure out how many amps of current, which is I, how many amps of current are going through the circuit. What I'm going to do is I'm just going to put this equation up here because it's in everything. Current, or voltage is equal to current times resistance. So if we're looking for the current, that's this. Current is going to be equal to voltage divided by resistance. You're just rewriting that equation. So yeah, 12 divided by 3, voltage divided by resistance, you get 4 amps. There you go. So if your parents, like mine, used to have old Christmas lights, they were wired in something called series. What is the bad thing about something wired in series? Like,
Well, because it's in series, if one light gets taken out, then you pretty much remove the connection for all the rest.
that's right.
It's all just
One goes
one
out.
after the other.
Yep. If one light goes out on something that's wired in series, none of the lights work, which makes changing a bad bulb very hard. Because you have to take a bulb that you know is good, and you have to put it into every single socket till you find the one that's bad. And here's how things are wired in series. This is an example of 2 lights that are wired in series. There's only one path for the current to go. And if you interrupt that current by breaking a light bulb, it just gets stopped, and it can't get back to the battery, and this light is not going to light up. This is something wired in parallel. We'll talk about that in a second. Here's another example of something wired in series. There's only one path for that current to go. If there's only one path for it to go, then if it gets interrupted, then none of these lights are going to work. Everything goes out if this light dies on you. And I don't know how much experience you guys have with these little light bulbs, trying to yank them out of those tiny little sockets. That's an easy way to get rid of all your nails or bend them all back, because they're so hard to get out of there sometimes. You can tell I'm a little bitter with series circuits. So if you want to, here's the thing. Let's say you want to figure out the current in this circuit. You've got 3 different resistors here. So how is this equation going to work if you've got 3 different R's? Well, what you do is you have to find something called the effective resistance. You have to basically say, when you combine these resistors, what is their combined effect on the whole circuit? And the way you combine them is different based on what your circuit is. If it's in series like this, you just add them up. 5 plus 10 plus 3 is 18, which is probably what the next slide says. And I'm not getting Okay. Oh, it was Santa.
Santa?
Yeah.
You realize he's gotta be eternal, he's been around for 400 years and he's still giving out candy and stuff.
And you know what you don't realize with Santa is, he's got all these elves that make all these toys. He must have a coal plant too. Because if he's also handing out coal, he must have a big supply of that somewhere.
I think that as much as you say oh, you're a bad kid, you're gonna get coal. I know that doesn't really happen. I feel like he's real soft.
He probably is.
You get coal, but you don't actually get coal.
Soft as his own beard. So, yeah, if you want to figure out the current, you'd want to find the overall resistance here. And if you've got something wired in series, you just add them all together. You get 18, so now you can solve this equation. If you're looking for current would be voltage divided by resistance, and you plug the numbers in, you get 0.5 amps. That's how you would figure your current for this kind of a problem. Then, there are new lights that are now wired in parallel, thankfully. And all your Christmas lights pretty much now are wired in parallel, which is not only easier to deal with, but it's also much safer. This is something wired in parallel. If this bulb goes out, it does not have to pass through it. The current can just take another route to get back to that battery. Same with these up here. If this bulb goes out, the current has another route it can take to get through it. It's not just stopped like it is if something is wired in series. Now, when we're looking And an example of this on a circuit diagram like that, the way that you wire something in parallel and you show it here makes it look like this. You've basically got like ladder runs. And if you think of it again like water going through a piping system, the water can travel all different ways. If this resistor stops working, if the light bulb goes out, the water can still pass through these pipes and get back. And so it's wired in parallel. Now, if you want to figure out your overall resistance here, like we did in the last one, something wired in parallel, you got to add up their inverses. And when you add up their inverses, and then take the inverse of that, in this case, you get 0.625 ohms. So then this would be your effective overall resistance, and you could use that to calculate current, just like we did in the previous example. Questions? Are you guys on board? This is great. Awesome. If you're still kind of on board, that's good too. Now, power is just something we'll talk about quickly. Power is just one extra equation you would add to the mix here. Basically, if you have any two of these three numbers, you can calculate power. Power is a measurement of how fast energy is being delivered to a resistor. It's measured in watts. We eventually talk about that when we get to energy. But there's three different equations because there's three ways you can calculate it based on what information you have. And so it's just a matter of plugging those numbers in if you have them. So this was the circuit that we dealt with in series. This is all the information we know already. So if we want to calculate power, we know the current. We calculated it to be 0.5 way back in the day, a couple minutes ago. And we know the voltage is 9 volts. It tells us that. So the power is just that times that. It gives you 4.5 watts. It's just a matter of plugging numbers into an equation. You can do the same thing for the parallel circuit. No surprise there. Watch closely. Did you notice anything?
It went on for like a second after.
Yeah. After I unplugged it, it kept going for a little bit. You see that? One more time.
Some brandy in it too.
You can forget about the brandy. But yeah, as soon as I unplug it, it still goes for a little bit. And so the question is, why is that? And that happens because of something called capacitors. So resistors are things like light bulbs or anything that a current might make work. You know, usually it's a. Was that the door?
So,
Yes. You're like Mr. Rogers. Oh, sorry. It's a speedy delivery. Thank you. You found the dumpster okay? Okay. Gotta do something with the body. So, capacitors are the exact opposite of resistors. Resistors use energy, and capacitors actually store it. And so the reason you could still hear that music is because there were capacitors in that radio. And when I unplugged it, yeah, they lost their charge, but it took them a half second or so to do that. They store charge. So they're the exact mirror image of a resistor in more ways than one, actually, as you'll see. It's just a device that stores charge. You measure capacitance in farads. And whereas a resistor is a squiggly line Charlie Brown t-shirt, a capacitor is two parallel lines that are the same length. That's how you would represent it on a circuit diagram. So, this is actually pretty easy to understand. Capacitors, if you wanted to add them all up, what you do, if they're in series, is you add up their inverses, which is the exact opposite of what you do with a resistor that's in series. So what do you suppose you do for capacitors that are in parallel?
You add them.
Track them.
Just add them up. Yep. So it's the exact opposite way that you deal with resistors. That's all you got to know about capacitors. Okay. We're going to take one more step into the woods here, and it's going to get a little bit complicated. And then we're going to take a step back and see how much complication you guys can handle. This is going to be fun. So, nothing to lose. No test, no homework, whatever. No quiz. So let's see how we can do this. And if you have questions, let me know. So let's say we want to find the overall effective resistance of this circuit. Now this is a complicated circuit because it is both a series circuit and a parallel circuit in one. We know that because, I'm going to just keep coming back to this analogy, but like the water in a pipe thing, the water has two paths it can take here, but when you get here, you only have the one path. All the water, all the current has to go through this resistor. So this one's in series, these two are in parallel. So how do you find the overall effective resistance of that? Well, what you got to do is you have to figure out what the overall resistance is of these that are in parallel. And you can do that. We did that already, actually. 1 over 3 plus 1 over 6. And you take the inverse of that, you get 2 ohms. Now, it's basically saying that this is one resistor that is in series with the rest of this. We're essentially saying now this is like one big resistor. Like instead of having 2 lines here, we've just got one. And then it would be like a 2 ohm resistor being right there. You wouldn't have this over here. You're essentially saying this is one resistor of 2 ohms. And then it's like having a circuit that is in series. You add 2 plus 5, you get 7, and you get your overall effective resistance. So yeah.
How did you get 2 from the 6 and the 3?
These are in parallel, so we have to do 1 over 6 plus 1 over 3. And I think we did this on a previous slide. And then we take the inverse of whatever that number is, and that's how you get your 2. So then once you have your effective resistance of 7, 2 plus 5, you can then use that same equation that we go back to every single time in order to figure out your current. We know the voltage, it's given to us. We know our overall resistance, we figured it out, and we do the division. 0.25 amps is your current. If you can follow this at all, this is basically like being 1 or 2 weeks into this in terms of homework and stuff. So, if you're on board whatsoever, give yourself some credit. Now, this is where we also get kind of complicated, but at least this part's going to make sense. Sort of. What about the current at other spots in this circuit? We know all the current has to pass through this place. So that current that we calculated, 0.25 amps, is going to go through here. But here it's divided up in these 2 paths. So you're going to have some current this way, some current this way, and in the end they both have to add up to 0.25 because they're going to come together here. But what do you suppose the current's going to be in these 2 positions? Higher here and lower here? It's actually going to be the opposite, because this resistance is like something that makes it hard for the water or the current to pass through this spot. So if this is twice the resistance here, you're going to have half the current passing through it. So this is half the resistance, so it's twice as easy for the current to go through this place. So you're going to have 2 times the current here compared with there. And then it's, I'll let you read this. I suppose I could have just thrown up the slide. So 2 times the resistance here compared with there. So the current traveling through here is half, because it provides twice the resistance, than the current traveling through this one. Therefore, mathematically, the current going through 6 is going to be half the current going through 3. And we know that when you combine these currents, you're going to get 0.25 amps. So, let's just do some substitution. if this is equal to I6, let's just put this in for I6. And that's where you get this. Now you've got one equation with one unknown, and you can solve for I3, current 3. Ultimately, you end up with 0.167. Questions? I know it looks so complicated and everything. Science plus math equals difficultness sometimes. Okay. So, this is we're getting to the end of the difficult part here, and then we jump into a whole new ship, which is kind of fun. But if we know that's 0.167 going this way, all we got to do is subtract that from 0.25 in order to figure out how much current is going through here, because they have to add up to be 0.25. So when you take the difference, you figure out how much is going through that part, and you get 0.083 amps. Going through this part, I should say. So yeah. One more thing. Okay. Voltage drop. So this is your battery. And this voltage, to make these little light bulbs turn on, this voltage gets dropped off at each one. And sometimes you might want to figure out how much of that voltage is dropped off at each. And that's something that we can solve for. So first off, we got to figure out how much of that voltage is going to be lost between those two resistors there. And then we're going to look at that animation again. Nice. That is very satisfying. I don't know about you guys. So the rest of the 1.75 volts after this is going to be dropped off at the 5 ohm resistor. So if we want to figure out that voltage, we got to figure out how much goes to the parallel part of the circuit. And then after that, we can deal with how much is lost in the part that's in series. So this is like the last difficult part before we talk about something different here. So in order to do this, we know the overall resistance of this big circle is 2 ohms. We did this several slides ago, quite a while ago. So 2 ohms is this overall resistance. So now we've effectively got a 2 ohm resistor here and a 5 ohm resistor there. And we want to figure out how much of that voltage is lost here compared with here. So this is like one big 2 ohm resistor. This is like the regular 5 ohm resistor. So if we want to figure this out, we just do a little bit of subtraction. Voltage is equal to current times resistance. So the voltage going through 3 and 6 is going to be equal to however much we start with minus the product of the current and the resistance. Because when you multiply these, you get voltage. So you just take the difference. We know that 0.25 amps are going through our current when you combine these together. And so when you multiply that and you take the subtraction, you get 1.25 volts. So this is how much voltage is dropped off combined between these two circuits here. 1.25 volts. So now we can figure out how much voltage is dropped off at the 5 ohm one. Same method. We start with 1.75. From that, we subtract the product of the current and the resistance. 5 ohms times the current, which is 0.25 amps. And when you do that subtraction, you get 0.5 volts. And they add up to 1.75, which is great, because that's what they ought to do. So overall voltage here plus the overall voltage here should be 1.75, and that's what we get. Wonderful. Now, what if we want to figure out how many volts are dropped off at each of these resistors? This is the part that's actually easy, because we know 1.25 volts get dropped off between the two. If you actually want to figure out how much gets dropped off at both, the resistances don't matter. It's just equal. So 1.25 divided by 2 is going to be equal to 0.625. So that gets dropped off at each of these equally. So yeah, it's about as deep as that goes. about 2 weeks worth of circuitry. Now, yep. You guys like cereal?
I love cereal.
I do too. I don't eat it anymore, but I'm trying to be more healthy, so I actually eat oatmeal that doesn't have sugar in it. Tastes like cardboard.
That should make me feel better about myself.
But I miss the days of cereal. When you're young, you can still eat this stuff, and it's like doesn't affect you at all, you know. But when you get older, you kind of gotta get healthier. So, what are your favorite cereals? Yes.
Frosted Flakes is my favorite.
As long as they don't get soggy, I like Frosted Flakes.
Yeah, you just gotta eat it fast.
However, it's kind of like, how many of you guys like Captain Crunch?
Captain Crunch, you have to let it soggy or else it'll destroy you.
Exactly. Yes, you need Captain Crunch to be a little bit softer. At least I do. I like it better that way. But yeah, I miss having my Cookie Crisp, my Lucky Charms, Cinnamon Toast Crunch.
There's nothing more gross than soggy Cinnamon Toast Crunch.
Ugh, yeah, the real soggy. If you can still taste the cinnamon, it's okay. But the super soggy is
milk after it's all cinnamon.
yeah, good times.
That was the cinnamon milk. Yeah.
Now,
I'm a big fan.
this part here is university level. There are very few, if any, high schools that actually teach Kirchhoff loops. I want to see how long you guys can stay on this train. Because it looks complicated, and it is. But if you just take it one step at a time, it's not too bad. So see if you can hang on to your seats for this here. So eventually, you might have to solve for things where you've got circuits that are super complicated. You've got two batteries. You've got something that's in parallel and series. So this is a rather complicated circuit. And the way we deal with that is by going in circles. And that's all we do. We go in circles, and we use this equation, which I erased for some reason. So let's see how you can keep up here. So here's circle 1. This battery is producing a current, and some of that current takes this path around this big square. Essentially, any place you have a square, you make a little circle in. And you follow that circle, doing this equation all the way around. V, voltage 1, is equal to the current times resistance. Now, if I'm going in this way on my loop, and it would tell you the direction that the current's going. If I'm going this way, I eventually get to this resistor. So it would be like I1 times 2 ohms. But there's also this current going through this resistor. They're going the same direction. So, yeah, kind of, yeah. You would have to add these two currents and multiply that by that 2 ohm resistor. So I1 plus I2 times 2 ohms. I'm sure the next step would put the numbers in. And then you get to this resistor. This is in series. It doesn't have anything to do with this current. So it's just I1 times R1. And then those numbers go in right here. Yeah. So 28 volts equals what I just said with this. Let's do this one, and we'll just see that. And then we'll get to a really complicated one. So 7 volts is equal to current times resistance. So we get to this resistor. These two currents are traveling the same way, so we add them together. And we multiply them by 2. So that's what this is. And then we get to this resistor here. This one only encounters current number 2, so it's just current 2 times 1 ohm. And this is enough to figure out your answers. It just becomes a math problem after this, because you've got 2 equations and 2 unknowns. So yeah, I'm not going to go through the math part, but that's how you'd set it up. This is where the physics ends and the math would begin. Now, you want something real complicated, check this out. Now, this is like the sort of thing that you would have in an advanced physics college course. So let's just see if you can at least follow along here. We want to make loops out of this. They're called Kirchhoff loops. And once we make those loops, we can make equations that we can solve. So let's look at loop number 1. We start with the 10-volt battery. And this loop eventually gets to this 1 ohm resistor. So current 1 times 1 ohm. Right there. Now we get to this one, 25 ohms. So it's going to be current 1 times 25 ohms, but there's also this current here. These currents are going in opposite directions. So instead of adding them, we subtract them. So current 1 minus current 2 times 25 ohms. That's where that comes from. And then we get down to this resistor here on our path. So current 1, and now current 3 is also traveling opposite, so we got to subtract those two. Current 1 minus current 3 times 50 ohms. That's where that super long, crazy looking equation comes from. You're just drawing circles. So then we got to do the other two. And this is the last part of it. After we finish these two, I'll put up some cool Christmas light pictures. So current 2, there is no battery here. So we start with 0 volts. And if we start with this resistor, you can start anywhere. But current 2 is going this way. Is current 3 going the same or opposite direction?
Opposite.
Yeah, they're going opposite.
So minus.
Yep, current 2 minus current 3 times 1 ohm. Yep.
Plus 2.
And here, we've got the 55 ohm resistor. So this is by itself. There's no other loop there. So we've got current 3 times 55 ohms. Oh, sorry, I'm on the wrong loop.
Yeah.
Yep. My bad. So next we've got the 25 ohm up here. So this goes opposite directions. So just like before, current 2 minus current 1 times 25. And finally the 30 ohm. Current 2 times 30, because there's no other loops to deal with there. And finally, the last part. Loop number 3, which I really wanted to get to for some reason. We've got the 50 ohm resistor here. It's going in opposite direction as current number 1. So that's going to be minus current 3 minus current 1 times 50. Then we get to this resistor. They're going opposite directions. So current 3 minus current 2 times 1 ohm. Yep, 55 is by itself over there. There's no other Kirchhoff loop involved. So current 3 times 55 and is the current. Yep. So now you've got yourself 3 equations with 3 unknowns. Insert some fancy math, and you can solve for all 3 of those.
Oh. It's only one side.
Right? Why did I turn all the lights off for this, huh? Imagine that electric bill. Oh, this is actually, I just Googled those other two. I actually took this one myself along with, I think, the rest. These are from Celebration of Lights in Oshkosh, where you drive through, turn your headlights off, and you get to see this really cool light show in a park. And this is one of those things where they set the lights to like a song that you tune your radio to. Really fun stuff. Another little tunnel there. Another one there. These are all Celebration of Lights. And this is the last one. I really like this one. These are probably my favorite Christmas lights. You guys know what these are? Those like blue icicles that like drip. I have a bunch of these that I put up on my house. I think they're so cool looking. And this guy had like a whole bunch of them through all of his giant trees, and it just looks so cool. So there you go. Circuits.
Wait, is that his house?
Yeah, that's a house.
Oh. I thought it was a winter.
Winter Wonderland.
Alrighty.
Oh, keep the lights on.
Tomorrow we're going to start our next unit.